Okay guys, I am going to attempt to show you how two equations that I've been getting some questions on are related. And this is basically the two different equations that you can use for calculating cell potential, one of which uses RT over NF, natural log of Q, and the other one uses 0.0591 volts over N times the log of Q. So I'm going to write that out real quick. So these two equations are both going to be equal to your cell potential. And so the first one, the most common form, or the original equation, if you want to think about it, is the standard cell potential minus RT over NF times the natural log of Q. Now this equation, when you are at 25 degrees Celsius, so anytime you see a problem where you're going to use this equation but you're at 25 degrees Celsius, you have the option of using this simplified equation, which is still going to be the standard cell potential but minus 0.0591 volts over N log of Q. And so the confusion's been coming around the fact that people are unsure, obviously, when to use either of these forms to calculate E. And also why it is that if this equation is just having 298 Kelvin plugged in for temperature and then solved to give this equation, why is it that you have a natural log of Q here, but a log with a base 10 of Q over here? And so I want to kind of show you where that's coming from. So the first thing is I want to prove to you that if you plug in values for R and for temperature and for F in this component of this equation, that doesn't give you 0.0591 volts, right? Because you might be looking at this and think, okay, well, R times T over F should give us this 0.0591 volts. So if I write out R times T over NF, and we plug in the values for R, T, and F at 25 degrees Celsius, we'll have 8.314 joules per mole Kelvin times 298 K, since we're at 25 degrees Celsius, all over N, which we're just going to leave it alone right now because I'm going to show you how we're going to get from here to here, basically. And then our value for F is going to be 96,485 coulombs per mole of electrons. Now, if we multiply all of this out and simplify it, okay, we're going to have 8.314 times 298 divided by 96,485 is going to give you 0.02568. And now for our units, we have joules sticking around, right, because we don't have anything to cancel that out. We have per mole Kelvin here and Kelvin here. So this Kelvin and this Kelvin are going to cancel out. So that leaves us with joules on the top. And then on the bottom here, we're going to have coulombs per mole of electron. Now N is going to have a unit of per mole, or of moles of electrons, and so that unit is going to cancel out when we have the N on the bottom. So I'm just going to go ahead and simplify this and say that this is basically 96,485 coulombs. So that would make the units for this value joules per coulomb, and joules per coulomb is the same as volts, right? So we're going to get 0.02568 volts. And now remember, we're not doing anything with N here, so these values are still all over N. Right? All right, so how this works out is RT over NF when you're at 25 degrees Celsius gives you 0.02568 volts over N. Now this is definitely not the same thing as this 0.0591 volts over N that you get up here. And so the difference between these two numbers is coming from this fact that you have a natural log for this equation and you have a log with a base 10 for this equation. So I'm going to go ahead and set those equal to each other, and then we're going to see what that actual difference in these two numerical values, this 0.02568 and this 0.0591, ends up being. So if we take the 0.0591 volts over N times log of Q is equal to our 0.02568 volts over N times the natural, whoops, did I get that right? Yeah, natural log of Q, okay? So now we have an N on both sides here, which basically just cancels out. And then we have this 0.0591 and 0.02568. So I'm going to go ahead and divide both sides by that 0.02568 volts. And so 0.0591 volts divided by 0.02568 volts is going to give us 2.3. So it's going to be 2.3 times the log of Q is equal to the natural log of Q. Okay, so does this difference in the two types of logs end up giving a value of 2.3? Well, if we think back to log rules, especially those for changing base, I'm going to start off with saying that ln of Q is the same thing as the log with a base of E of Q. Okay? And so log of Q up here, log normally, most typically, especially since your calculators are programmed this way, has a base of 10. Right? But natural log is just a log with a base of E. And so the way you switch back and forth between different bases comes about by this equation, where if we have this log of E, log of Q with a base of E, and we want to change that to log with a base of 10, so log Q with a base of 10, then that is going to equal log with a base of E of Q over log with a base of E of 10. Okay? So this is just, you can look this up on Wikipedia if you want to for how to change bases, but basically whenever you have a statement like this where you have this log with one base for a certain value, if you change to log with a different base, it's just your original base for that value times the, or divided by the original base of the new base. I know it's kind of weird, and I'm probably saying this really confusingly, but if you go look this up, this is just a general form of how to do this. So I'm going to put this back into natural logs because writing things out with these bases looks very strange usually for people. So all of these logs with the base of E, it's the same thing as writing the natural log, right? So this whole expression goes from this crazy sort of thing with the bases written in to natural log of Q over natural log of 10, right? And then this is equal to, so I'm going to again say, normally we don't include this base here, and normally log is considered to be with a base of 10. So there's no point in including that value there as long as we are establishing that log will normally have a base of 10. So ln of Q over ln of 10 is equal to log of Q. Okay? So now we have this relationship that's going to get us back up here, right? So if we write this in terms of what ln of Q is equal to, right, we're going to have ln of Q is equal to log of Q times the natural log of 10, right? So we're going to take natural log of 10, multiply it to this, and move it to this side. So multiply it on both sides. So ln of Q is equal to ln of 10 times the log of Q. Okay? And if you take your calculator and find what ln of 10 is, it is 2.3. So natural log of 10 is 2.3, and that is where this 2.3 is coming from for the difference between these values. So hopefully that sort of helps you guys understand a little bit why you have these different logs being used for the different forms of this equation. The main take-home point here is just that you want to make sure that on your equation sheet for the exam that you have the right equations written down. I think for the one worksheet they forgot to actually change the one equation to either log or to natural log. They had them both expressed as the same thing, and that is definitely not correct. So you want to make sure you have them in the right spots, and you also want to make sure that you're using them appropriately. So again, just to reiterate, the form with the 0.0591 volts is the equation with the temperature being 25 degrees Celsius. So this just simplifies the equation so you don't have to plug as many values in. You can always use the original form of the equation and you will still get the same answer if you're at 25 degrees Celsius for either of these. Just be sure not to use this one if you're not at 25 degrees Celsius. All right. If you guys have any questions, you can post them in the comments if you want, or you can send me an email. Otherwise, I hope this was helpful. Sorry this video ended up being so long. Maybe I'll make more of these to come if there's other issues people want to see done out on paper. All right.